Get started. So, Sheaves form a topos, part 2, take it away.
All right, well, thank you everyone. So in this talk, I'll be delivering the second part of my journey through the topos structure on pre-sheaves and sheaves. So last time, we saw that the pre-sheave category is a topos. So PSHC being the pre-sheave category. It has a topos structure where limits and co-limits are taken pointwise. So limit of a diagram of pre-sheaves at an object C was just the limit in sets taken this way, pointwise, and the same for co-limits. And then we also saw that there is a subobject classifier in pre-sheaves given by taking all sieves on a given object, so the set of sieves. Then finally, we saw that the exponential in pre-sheaves, which is the most complicated part, was given by taking two pre-sheaves and an object C that was a set of natural transformations from the representable functor of C times F into G, where this product is taken the same way this limit is taken, so taken pointwise. So then that showed us that pre-sheaves form a topos. After that, we decided that we wanted to show that sheaves were a topos, so we needed some form of bridge. And we discussed the process called sheafification, or the associated sheaf functor. So what we arrived at was a theorem that there is an adjoint pair, A, going from pre-sheaves C to sheaves on C with the chosen growth and deep topology. And that has a right adjoint given by the inclusion functor. So this just includes objects and morphisms into here. And this A, we found, was given by the double plus construction. Informally, this double plus construction basically adjoined the necessary amalgamations to matching families and then made sure they were unique. Okay, so in this talk we want to show that the category of sheaves forms a topos. So we're going to have to go through the same process, more or less. We'll show that limits and co-limits exist. We'll show that there is a subobject classifier, and we'll show that there is an exponential. So limits and co-limits we can actually do straight away as a corollary of this theorem. So in the category of sheaves on C, with a fixed growth and deep topology, a limit of a diagram of sheaves can just be taken pointwise. Just in the case, as in the case with pre-sheaves. Why is this the case? Well, it's because the inclusion functor, iota, is a right adjoint, so it has to preserve limits. So when we do this, everything passes over nicely. Moreover, this gives us a recipe, this theorem, of how to define co-limits, which on the face of things is the less obvious thing to define.
Actually, the adjunction only tells you that if you have a limit, then it preserves it. Actually, last lecture you showed finite limits existed directly, right?
That's correct, yes.
So I think that's what you're referring to.
Yes. Co-limits is... For co-limits, then, we get a recipe from this, given by, we take our diagram of sheaves, then we know how to define co-limits in pre-sheaves, so we're going to include this diagram into pre-sheaves, pointwise. Then we apply our co-limit, and then we get a co-limit in pre-sheaves, so this is well defined. But this may not be a sheaf at this point, so then we apply the sheafification functor. And we take this as our definition of the co-limit of the diagram at C. So in particular, from this corollary, there's actually two immediate results about the structure of the category of sheaves, which are totally sort of unobvious on the face of things. So in particular, we know that there is a terminal object in the category of sheaves. this shows that the pre-sheaf 1 of C, just giving the 1-point set, the terminal set, that's the terminal object in the category of sheaves. And moreover, we know that a morphism F.
The C on the right hand side is superfluous. I mean, it's the code of the F1, it's A.
Moreover, we know that a morphism of sheaves F from curly F to G, that is monic, it's a monomorphism in sheaves, if and only if the associated morphism of pre-sheaves is a monomorphism.
So you've got C on the left-hand side of that definition, curl C of Fi.
Yep.
Do you want that there?
That's iota. We've included Fi into. Oh, is that what you're saying?
That's right, on the second line.
Yeah. I think you read an iota as a C. Do you mean like?
I'm not quite sure what
So if on the second line, on the left-hand side of that definition,
that's an iota.
it's an iota there.
Yeah.
We've got elements in sheaves, similar.
So we can immediately define monomorphisms now in the category of sheaves, just by monomorphisms in pre-sheaves. This is because the morphism is a monomorphism if and only its kernel vanishes, and then we can compute this using this formula over here. I've got to warn you though that this does not hold for epimorphisms. This fact is actually sort of a fairly geometric fact that you might know. So if you had, say, functions on the Riemann sphere, then we know from complex analysis that locally we can define as lots and lots of holomorphic functions on the local patch. But we also know from complex analysis that there are no non-constant holomorphic functions in the Riemann sphere. So then morphisms of sheaves, so the sheaf of holomorphic functions, they might be locally surjective, i.e. they might be surjective, say, in pre-sheaves, but they won't be globally surjective. So this is sort of an example of a nice way in which category theory of this stuff reaffirms what we know geometrically, which is what we all like to hear. Right. So straight away, we're making some pretty good headway, showing that the category of sheaves forms a topos. We've already got the limits and the colimits that we require. Moreover, we actually have some stuff about the structure of the category of sheaves. So we have a final object, which is going to help us to define a subobject classifier. And we know what monomorphisms are. So this also helps with the subobject classifier. So the next task at hand, the next easiest thing to do will be to define exponential objects in the category of sheaves. So we might naively hope that we can define exponentials in the same way that we define them in pre-sheaves. There's not any particular reason to hope this, but we're young and we might think that's true. It turns out that this intuition for once is actually nice. It's encoded in the following lemma.
Mathematics hasn't disappointed you yet.
So if we take two sheaves, F and G, and suppose that an exponential exists. So we're not claiming that one exists at all, but we take a supposed exponential. So we write G to the F to the bar for some conjectural exponential. Then in fact, once we include that exponential into pre-sheaves, it has to look like the following. So iota of the exponential object is going to be isomorphic to iota of G to the power of iota of F, the exponential object of the two pre-sheaves associated to these sheaves. It's a fun sort of exercise to see why this is true. So let's take H to be a pre-sheaf.
Sorry, so what do you mean by
Yeah, so what this will say is, that the definition of an exponential, if it were to exist, has to match the definition in pre-Sheaves. So take H to be just some pre-sheaf on C. Then we know that any morphism, H to iota of the exponential object, is going to be adjoint to the a morphism from the sheafification of H to the exponential. Now, we know the exponential is characterized by an adjoint property. So this in turn means that this is adjoint to a morphism from the sheafification of H times F into G. Okay. Now in this step we're going to be a little bit clever. So we know that the sheafification functor preserves finite limits. So in particular we know this left-hand side is actually equal to A of H times iota of F. But this also follows from the fact that once you take a sheaf, take its underlying pre-sheaf, then sheafify, you're going to recover the sheaf that you started with. This is because sheafification of a sheaf is the sheaf again. So this is actually adjoint to a morphism from the sheafification of this product pre-sheaf into G. But then we can apply the adjoint property of sheafification again to show that this is a morphism from H times iota of F into iota of G. And then we finish by showing by concluding that that's adjoint to a morphism H into iota of G to iota of F.
So Patrick, you said that the sheafification of a sheaf is the sheaf again. Have you used that fact in the very second line as well? You see how the iota, I assume you provide an A to this and without get the original sheaf to start off with, or are you using the property of adjoints there?
I'm using this, so these are all properties of adjoints. So this function, this morphism is adjoint to this. This is the chain of adjoints. I've only used it in this step to go from here to here. Okay, so we now know that the exponential is not going to be some great mystery in Sheaves, but in fact we can use the hard work we did in pre-Sheaves to write down at least a proposed definition. So now we're going to write G to the F of C to be the natural transformations from HC times F into G, just like we did for pre-Sheaves. Of course, we've actually only showed at this stage that taking two sheaves, an exponential object exists in pre-Sheaves, which we already knew. So we need to show that this will actually form a sheaf. This will be the last step in proving that exponentials exist. So if G to F and F are sheaves, then so is the exponential.
You want to leave out the bar in this case, don't you? I mean, you want to say the pre-sheaf exponential is a sheaf, and then it's fine to call it GF bar. GF bar stood for some putative exponential sheaves.
Sure, okay. I'll leave off the bar. Bar is staying. The bar is staying there for now.
It's gone in our minds. Yeah.
So this proof is going to proceed by a general strategy that we use whenever we're dealing with sheaves in any context. So this could be sheaves on some more wildly exotic context. Proof will take two steps. First, we'll show that if G and F are separated, so that is that if a matching family amalgamates, that amalgamation is unique, then so is the exponential. And then second, we'll just show that amalgamations exist. Then that will be sufficient by combining these two. So this is going to be our sort of blueprint for doing this type of proof now and later in the talk. So before we start doing either of these, it's helpful to write down what exactly we mean by an element of a section over this sheaf. So we take some theta. This is going to be in the exponential over c. What's this going to be? So it's a natural transformation going from hc times f into g. So by definition we'll say that it takes g from, say, d into c and some x in f of d, and it spits out theta of g x. So strictly speaking, we should probably put a subscript d under this theta, but it's just going to make our life hell if we try to do that, so we'll leave that off. But we'll sort of have that understood by context. Now, this isn't just a function, it comes with two relations, one imposed by naturality and one imposed by the pre-sheaf restriction that exists on the exponential. So the first relation imposed by naturality is that for h from e to d in C, we have the first identity that theta of g x restricted along h is equal to theta of g h x restricted along h. So observe actually that this means that, yes, so this is the restrict. So the naturality gives us this identity, which we'll make use of later in the proof. Then if we have some morphism, say f from c prime to c in C, then the pre-sheaf restriction, the restriction of this pre-sheaf along f, gives us the identity that for g prime, now going from d prime to c prime, and x prime now living in f of d prime, we have that theta restricted along f of g prime x is equal to theta of f g prime of x. Or in other words, theta restricted along f is just theta after hf times 1. That visible? Yeah. So our first step is to show that if f and g are separated, then the exponential pre-sheaf is going to be separated. It's going to turn out actually that we don't need f to be separated in this case. We only require g to be separated. And actually the whole proof follows if only g is a sheaf. But we'll leave the hypothesis as they are. Okay, so we're going to fix a covering sieve S over C. And we're going to take two elements of the exponential over C, theta and sigma. And we're going to suppose that they restrict to the same thing over each element of the cover. So i.e. that theta restricted to f equal to sigma restricted to f for all f in S. So implicitly what we're saying is that there is some matching family for this cover such that both theta and sigma are amalgamations. So using the second property over here, the second identity over here, this restriction thing means that for some g prime and x prime that we have over there, we have theta of f g prime of x is equal to sigma of f g prime x. So if we just take g prime to be the identity, we get that theta of f x is equal to sigma of f x for all f in S. Okay, so we're almost there now actually, because what we need to show is that this holds for all morphisms in C, and at this stage we've just shown it holds for all covers. So we'd like a way to extend this. Well, that's going to be done by using this first property, the property of naturality. So now we're going to take a morphism K from C prime to C, and X now in C prime. Then for any G prime in the pullback by K of a covering sieve S, we're going to have that theta Kx restricted along G prime by naturality is going to be equal to theta of Kg prime x restricted along G prime. Now we're in the territory to apply this. So then we have that sigma of Kg prime x G prime. These are equal. And now this then means that theta of Kx restricted along G prime. So we have this equality over here. But now observe that K prime of S, this pullback of the sieve S, is a cover of C prime. So since we assume that G is separated, these guys form a matching family. But then that means that both theta of Kx and sigma of Kx amalgamate this matching family. So in symbols, both theta of Kx amalgamate this matching family theta given like this. But then since G curly G was taken to be separated, the amalgamation has to be unique. So theta of Kx is equal to sigma of Kx. Now for any K, any morphism into C. But then of course this means that theta and sigma are equal, because we took K and X to just be arbitrary. Okay?
We only need G separated.
Sorry?
We only need G separated.
Yes, yeah.
You actually assumed the F was separated as well.
Yeah, I made a comment on that earlier. Those have made superfluous assumptions. Okay. So now all that remains is to actually show that amalgamations exist for all matching families. Okay, so once again, we're going to fix the covering sieve of C, and we're going to take a matching family theta sub f, so it's the matching family of the exponential over S. What we need to do is construct some theta over C, which restricts to each of these. So the matching condition, using the identities which are now erased, implies that whenever the composition makes sense, theta of f composed with G, Hx, which is exact by matching is equal to theta of f restricted to G of Hx, which was just equal to theta of f of gh of x. This is for any x in f of domain of G. So to find some amalgamation, we need some theta going from hc times f to g, and we need that theta restricted to f is equal to theta f. It turns out that it will actually be sufficient to take theta prime going from hc times f to g plus. And we hope, and such that the following diagram commutes. Take left-hand corner hd times f to g. Then we have an induced morphism hf times the identity going to hc times f. And then we have theta prime down the bottom. And finally over here we have eta g, which we defined last lecture. So to recall that, eta g is going to take x inside g of c and pump out the matching family of the restrictions of f of x to every possible cover. So we're going to show that this diagram commutes. Why is that going to be sufficient? Well, because we've taken G to be a sheaf, which means that this is actually an isomorphism. So the amalgamation is actually provided by taking theta composed with the inverse here.
So we take it suffices to find.
Yes, yeah. So instead of pulling sort of out of my ass some theta prime, which makes this work, which is often how things go in this type of thing, I'm going to show you how you can kind of discover this theta yourself when doing a proof. It's more instructive to look at it this way. So let's take some k and x, which feed into the top left-hand corner. And let's see what happens when we go down the clockwise. So going clockwise on this diagram, k of x is going to map to eta of g times, composed, with theta f of k and x. Then this is going to be equal to eta g of theta x, theta f of k x. Okay, so we haven't gotten so far. And then this is going to map to matching family theta f of k x restricted along h for when now h is in T of D. Works? Yes. Let me just check for a moment. T of B, where K was from B to D at the start. So then we know, and then, okay, what we also have is going forwards, so anti-clockwise, we have theta prime of K and X, theta prime of HF times 1 of Kx has to be equal to theta prime of Fkx. So now looking at this, we can actually pick this apart and reverse engineer exactly what theta prime needs to be. So without spoiling too much fun, I'll tell you right now that we can define Now for j from b prime to c and x in f of b prime, we'll define theta prime of jx to be the matching family, theta of jh with arguments 1 and xh, where h now lies in j star of s. Okay, so all that remains is to do a quick check that this actually satisfies this condition. Then indeed, we'll have that theta prime equals to hf times 1 of kx is equal to theta prime of fkx. This is equal to the matching family theta of fkh of 1xh for all h in fk star s. But now we know that f was taken to be a cover, so this is actually the maximal sieve. This is just equal to fkh of 1xh for h in tb, which is precisely what we get going in the forward direction. So we're done. We've given ourselves an amalgamation. So now we have an object which was the exponential object for pre-Sheaves.
Or maybe you said this out loud, but so in writing that definition down, you're taking k to be 1, and then starting from that calculation there with the restriction along h, and then using your identity up there to put the h into the subscript.
Yeah. So now we've given ourselves an exponential object which was the same as the exponential in pre-Sheaves, and now we've actually shown it as a sheaf. So we've sort of settled that part of the problem. So the last thing we need to do is to define a subobject classifier in Sheaves. Now, so far, mathematics has been pretty nice to us, and we might expect that this sort of kindness will continue. But unfortunately, we can't actually just write down subobject classifier for pre-Sheaves and show that it's a sheaf. We're going to need to take some sort of specialization of that idea. So why is that the case? Well, just as a quick diagrammatic sketch, suppose we had just two objects in a cover of a third in our category C. And suppose we took a sieve over this object and a sieve over this object. Then if taking sieves over an object formed a sheaf, any sieve on this object which restricted to each of these would have to be unique. But then as soon as we have more than one arrow for either of these objects to this final one here, we're not going to get a unique sieve. So for instance, the sieve that is each of these, the union of these plus these two arrows, that'll certainly restrict down to these two sieves. But then the other sieve, which is that instead of having that arrow, you had that arrow, or even both, will also do that. So the amalgamations aren't going to be unique. What this shows is then that we need some restriction on the sieves that are allowed to make this happen. So to arrive at that restriction, we're going to take a little step back and remember that in a site, a morphism f from D to C so taking more from F from D to C, and some covering sieve of C, then it's a fact that F is in S if and only if F star of S is a maximal sieve. This follows just by definition. Okay. So now we say that we sort of have the terminology of a sieve covering an object. It's quite natural then to take a generalization, the relative generalization, and talk about a sieve covering a morphism between two objects. So we say a sieve S covers F from D to C if the pullback of S by F is a covering sieve of D. And then with this definition, it's immediately obvious that if F is in S itself, then S covers F. But the converse is not true in general.
It's not the most clear notation of that.
Striking. So what we're going to do then, it turns out, is that to remedy this problem we had here, where we had basically an excess of sieves that we could choose from, it turns out that if we restrict to sieves where the converse is true of this statement, then we can actually form a sheaf. So we better give these guys a name. So we say a sieve S is closed if F is in S if and only if S covers F. I have to warn you that even though everything else in topos theory and this site business follows from terminology in topology, this doesn't have anything to do with closed subsets, even though you might be hoping it does. It actually refers to, when you take this in the topological case, you need to restrict to covers closed under all unions, I believe. Anyhow. Now, this doesn't actually just, okay, so we can now talk about taking object C and talk about all closed sieves on C. But we can actually say a bit more. So you can actually show fairly easily that given some morphism F from D to C and S closed sieve on C, then the pullback of S is also closed. This means then that we can actually write down a sheaf omega cool for closed on C, which we'll define to be a set of closed sieves on C. Pre-sheaf, sorry, I should say. We're going to show that this pre-sheaf is actually a sheaf. Spoiler alert. And this is going to be our subobject classifier. So before we try to show that this is a sheaf and that it is a subobject classifier, any category theorist in the room or hearing this would probably be screaming at me because I've talked about a general object, namely all sieves, and I've given you some really nice specialization, namely closed sieves. And all of you obviously desperately want me to give you a way to take any sieve and give you a universal closed sieve. I give the closure in a universal way. I'll do that first. So if S is a sieve on C, its closure is given by S at the hat, and we define this to be those morphisms H going into C such that S covers H. So as a sanity check, this is definitely closed. Why is that? Well, by definition, if we suppose that S hat covers F, then we know that by definition S covers S hat. So by the transitivity axiom, S covers F, and so F has to be in here. So it's closed. Well, I can also show, which I won't for time reasons, show that this is actually universal among closed sieves. So as a result of this, we have the following fact. The fact is that pullbacks and closure commutes. In other words, smallest, yeah. In other words, we take a sieve S and a morphism G, pulling S back by G and taking its closure. This is going to be equal to pulling back the closure of S by G. This is the crucial property that makes sort of everything work from now on. So the first port of call is to show that this is a sheaf. Once again, we're going to adopt our strategy of showing that it's separated first, and then we'll just show that amalgamations always exist. So fix the covering sieve on C, and take, say, M and N closed sieves on C. And we want them to satisfy, to restrict, to be equal in all restrictions over S. So in other words, such that G star of M is equal to G star of N for all G in S. Well, in particular, if we just take G to be the identity, this means that M restricted to S is equal to N restricted to S as sets. Okay. So the goal now is to show that M and N are actually equal. So take F in M. Then, of course, M covers F, and also S covers F because S covers C. Then M, F, and S covers F. All right. This means then that M intersect S covers F, because both of them do. But now by hypothesis, M intersect S is equal to N intersect S. So this means that N intersect S covers F. But then since N covers N intersect S, N also has to cover F. But then since N is closed, this means that F is actually inside N, and this means that M is inside N. Now we can just run this argument backwards, it's entirely symmetric, so we conclude that M and N are actually equal. All right? So now we know that omega cool is a separated pre-sheaf. Our last step is to construct an amalgamation. So take a matching family now of closed sieves. indexed by the cover S. Then the matching family means that G star of MF is equal to MFG, just symbols. Okay. So consider now the following sieve. We'll take M to be the compositions of F and G, where F ranges over all F in the cover S and G in MF. It turns out this is actually not going to be a closed sieve in general, but we're going to show that its closure is actually a closed sieve. So the closure is going to be the amalgamation we want. Okay. Well, immediately it's clear by definition that MF is inside M. MF is inside pullback of M. What we're going to do is we're going to show the other direction, and then we're going to use that closures and pullbacks commute. So take G in the pullback of M by F. So in other words, F after G was just in M. Then by the definition of M, since M is given by the compositions of these two elements,
This is supposed to be on the same.
immediately. Thanks, Dad. As you get too close to be able to see that words aren't real. Okay, so Fg is now in M, but M is given by compositions of this form. So actually, there actually exists some F prime in S and some G prime in M of F prime, such that Fg is equal to F prime G prime. And this means that MFG is equal to MF prime G prime. Okay, so now we just need to use some algebra. So by definition, this means that G star of MF is equal to G prime star of MF prime. But then we took G prime to be in F prime to start off with. This right-hand sieve is actually a maximal sieve, which means the left-hand side is also a maximal sieve. So that means that G is in MF. Yes, which is what we were trying to show. So this shows then that MF is equal to F star of M. Now we're not quite done, because as I remarked at the start, M isn't always going to be closed. But then, using the fact that pullbacks commute with closures, we have that F star of M hat is equal to F star of M hat. And now from this, we know that this is equal to MF hat. But then F was taken to be closed to start off with. This is just MF. And so M hat definitely amalgamates this matching family. So we have ourselves a sheaf. Mega cool. The last step is to show that this is a subobject classifier. So first, we're going to observe, just as in the pre-sheaf case, that a maximal sieve is, well, first a maximal sieve is always closed. So we can define a morphism true from the final sheaf, which is the same as the final pre-sheaf, to omega cool, just by the fact that sending C to the maximal sieve on C, just as we did in pre-sheaves.
C here just means the element of the singleton, right?
Yeah.
Which you're calling C.
Yeah, well, sure, we're evaluating this at C, and then we're sending the singleton to...
One of C is equal to like
The
C
C-
or something.
Yeah, yeah. This is the loose association. Not... All right. So our final lemma is that this monomorphism up here is a subobject classifier. For the category of sheaves. All right. Take two sheaves, G inside F, if G is a subsheaf of F. A particular G is just inside F as a presheaf. Then the proof of this is going to go exactly the same way as the proof in the category of pre-sheaves for the subobject classifier. So we're going to define a characteristic function by phi C. We define phi going from F to omega cool. It's going to be defined by phi C of X being those morphisms into C, such that X restricts along them to land in G. Now, if this is closed, this sieve that we've got here, the logic flows exactly the same as it did for pre-sheaves. So we'll leave that off the proof. If you need to see that, you can refer to the previous talk. So I'll just finish the proof by showing that this is closed. So take some f from D to C and suppose that phi C of x covers f. What does this mean? Well, then this means that f pullback by f of phi C of x is a covering sieve for D. Okay, so now what is the pullback? It's given by, let's see, the set of all morphisms into D. So this set is given by the morphisms H into D, such that F composed of H is going to be in phi C of X. Forgive me, there's a typo in the notes where I've written D in place of X at this point. And this, of course, is equal to the H into TD, such that X restricted along F, restricted along H, is in G of the domain of H. Well, now we have ourselves a matching family, namely the set X, F restricted to H inside F star of phi C of X. This is a matching family. This is not hard to check. And X restricted along F amalgamates this family. But we started off with G being a sheaf, which means that any matching family will definitely amalgamate, and that amalgamation is unique. And, the fact that this is a matching family is also because this is a covering sieve. That's the crucial point. So that this boy is a covering sieve of D. So then this amalgamates uniquely to X of F, which means that X restricted to F was in phi C of X the whole time.
This wasn't what I was expecting you to say. Sort of.
Hey, let me check that sentence. No. So that means that amalgamates to XF, which means so X restricted to F is inside G of D.
The conclusion has to be that F is in.
And so, yes. So then, yeah, this means so that amalgamates to that. But then this guy has to be inside G of D. So X restricted to F is inside G of D, since G is a sheaf.
The reason it's a bit confusing is because, of course, X restricted to F amalgamates that family. It's a restriction thing, but in F.
Yes.
And then you're saying that, well, because all those things are in G, all the pieces in the matching family at the top of that board, therefore the amalgamation also must be, there must be some amalgamation in G, and it can't be any other than X restricted along F. So therefore,
Yeah, so to repeat very fast what Dan said, because this pullback is a covering sieve of D, this means that each element of the matching family lies in G, and obviously X restricted to F amalgamates this, but then because G was a sheaf, this amalgamation is unique, so X restricted to F has to live inside G, which is this statement we've concluded here. But this just means, by the definition of phi C of X, that F is actually in here. So F was in phi C of X the whole time. In other words, if phi C of X covers a morphism, that morphism is inside it, so it's closed. So it's shown then that the category of sheaves also forms a topos. Thank you.